The topic of our research is knowledge-assisted comparative assignment of breast cancer using dynamic contrast-enhanced magnetic resonance imaging. Why the research of breast cancer is important? Because breast cancer is the most common female invasive cancer worldwide, and it is the leading cause of cancer deaths among women. In most expert societies, earlier detection of breast cancer by screen program is adopted to reduce the risk of breast cancer. TCE MRI is a welcome imaging-based diagnosis method which is non-invasive and has a high sensitivity and specificity. After the diagnosis, radiologists can express the disease grade as a score based on two different systems. One is Barrett's, another is Göttingen score. Here is the table, which shows the assessment categories. The DCE MRI as a dynamic modalities not only illustrates the spatial information like the conventional MRI, see the red figure. It also illustrates the temporal information, which reflects the contrast agent absorption and release in a lesion. We can see it in the red animation. The temporal information can directly be expressed as the intensity change of a lesion's voxel over time, which referred to as time intensity curve. Meanwhile, the signal intensity change percentage of a time intensity curve can be quantified by the relative enhancement, as this equation shows. There are three types at earlier and late post-contrast phase respectively, as a total number of 9 types. Based on the time intensity curves and relative enhancement analyzing, physicians can efficiently classify breast lesions or part of the breast lesions as benign or malignant. For the normal approach of breast lesion analysis via temporal information, it is very time-consuming and error-prone. Our purpose in this research is to create an approach that can speed up the workflow of analysis, provide a more comprehensive analysis processing, improve the reproducibility, and make full use of physicians' experience, like it is displayed in this mind map. In this section, I will elaborate the methodology and approach workflow. Our approach includes 4 parts: feature extractions, visualizations, fuzzy inference system, and visual confirmation. Let us start from the feature extraction process. First, we select one dataset from our database and load it. Then, all the lesions in the selected dataset are segmented by grab card method. As a third step, after a lesion is selected, its time intensity curves will be extracted and clustered by parallel optics method. When the feature extraction is finished, all the time intensity curve clusters will be transferred into next step, visualization and fuzzy inference system. And let us first introduce the visualization process. Here, we selected a malignant tumor as an example to show how we created the visualization. The up figure is a 2D view of the lesion. The down figure is a 3D view of the lesion. Its time intensity curves is shown in the right figure. The legend describes the following attribute of a cluster. The first entry shows the corresponding color. The second entry is the name of the cluster. The third entry is the number of voxels of the cluster. The last entry describes the relative size. When a representative curve is selected, its 50% region and the envelope region are shown. In order to illustrate the spatial characteristics of the lesion and its correlation with time intensity curve clusters, we create a chamfer with several bins to cover the entire lesion. The radius of these several beams is 5 mm. The number of the clustered voxels in each beam is plotted as histogram. We arrange the spherical histogram below the time intensity curve clusters plotting to provide a comprehensive observation and analysis. In order to compare two lesions, we arrange the windows side by side. The difference and similarities between two tumors can be explored. Then I will describe the fuzzy inference system. We created a lesion and a cluster library, and this library consists of two parts, a set of time intensity curve cluster and a set of lesion. The content of cluster set includes unique cluster names and their intensity values, like the figure shown. The content of lesion set includes the lesion name, score, and the subset, which stores the cluster index and its relative size. In order to build expert knowledge in fuzzy inference system, we translated the cluster relative size and lesion score into a natural language representation and regard as input and output variables, like the figures show. The knowledge is modeled in the form of linguistic rules, which have the structure of if-then clauses. Some of the rules are displayed in here. These rules are human-readable form, which can be saved in an external file. This allows physicians to share and adopt the knowledge with others. When a new lesion is put into the library, its time intensity curve clusters will be compared with the library content first. We employ the overlap coefficient to determine the degree of two clusters' similarity. If the degree is larger than 80%, the cluster of the new lesion will be merged by the cluster in library. Otherwise, it will be substituted. The comparison is shown as the right figure. In this example, cluster C1 is substituted by cluster 33. D is merged with cluster 21st. The relative size of new lesions are worked as input values, according to the process given in this figure. The prediction score in this example is 8, and the certainty score is 50%. The certainty score reflects how many clusters in new lesion are merged by the library. If the certainty score is low, it reminds that the physicians should be validated the result by comparing the input lesion with several node lesions. We come to the last process, virtual confirmation. In this part, physicians can confirm the result from our fuzzy inference system by using our virtual analysis approach. They can also examine fuzzy rules and comparing information of the new lesion with several node lesions. If physicians think the result is wrong, they can replace it. Otherwise, the result will be accepted. In the results and evaluation section, first, we show a comparison of a malignant and a benign tumor. For the right lesion, we can observe a clear upward trend throughout the entire course of time, while in the left lesion, C1 remains flat after 200 seconds. Both lesions are got correct prediction score. In this example, we compare two malignant lesions. The left lesion gets a correct prediction score, while the right is wrong. The cluster C1 to C3 of the right lesion shows a rapid increase with an continual increasing trend, making it more similar to the lower score lesions. Both lesion sensitivity score is rather low. It advises physicians to compare these lesions with several node lesions to verify them. Two benign lesions are compared in this example. The left lesion receives the correct prediction score, while the right one gets a wrong score. The cluster C2 of the right lesion shows a slower increase and a decreased trend after 350 seconds. This makes it more similar to the higher score lesion. We selected 14 lesions in our research and statistics the average time spending in the segmentation and clustering respectively. We also use one-fold cross-validation to test our fuzzy inference system prediction accuracy. The results are shown in the table. We can see it. There are 10 lesions got accurate prediction, and the other 4 are incorrect. So the prediction accuracy is 71.4%. The average segmentation time is 87 seconds. The average clustering time is 54 seconds. There are some feedbacks from a radiologist. She thinks our approach has the potential to deliver reproducible results and speed up the workflow. Well, here are some limitations for our approach. First, optics parameters epsilon has to be set manually. Second, the small objects are ignored in our segmentation process. Third, some spatial information such as morphology and textures are not involved. Fourth, the number of datasets we used was limited. In the last section is a conclusion. We create a visual analysis approach that arranges temporal and spatial information set by set, and by using our fuzzy inference system, physicians can make effective use of expert knowledge to provide a reproducible vision score. In the future research, we will make up the shortcomings and the limitations of the current approach. We also want to extend the cluster view with the third histopathological view. That's all. Thank you.